good morning, everyone. It's wonderful to see you all here, and it is a very special occasion today, being able to talk about and introduce the research of Etienne Garand, who is one of our very youngest faculty members, who is going to give us an overview about his research program today. So let me tell you a little bit about Etienne, and then we'll move to him. He got his bachelor's degree and also master's degree in chemistry in Canada. So I believe he's still a Canadian citizen. Yes. And so this was in Quebec at the University of Sherbrooke, where other than taking lots of classes and getting great grades, he also started research on vibrational spectroscopy of small alkanes, alkane ions, I believe. So this already gives you an idea about what he's interested in. Small molecules and the way they behave in terms of vibrations and other characteristics. So for his PhD, then he went to UC Berkeley and did research with Tenure, who is actually in the PhD of other faculty members and has a joint contribution of affiliation with our department. And over there, he also learned about how to build instrumentation in addition to working on small clusters, and he worked both on photoelectron imaging, and was probably a lot of the implementation of new equipment there, and also applied this idea of infrared dissociation spectroscopy, which is a really intriguing way to analyze the vibrational properties of small molecular clusters. And so, going on with this idea of analyzing small molecules in as much detail as possible, he did his postdoc with Mark Johnson at Yale. Mark Johnson was here not long ago. And some of you may remember about his work, where he's basically combining the infrared spectroscopy analysis of small molecules with cryogenic cooling, sometimes isolating these molecules and purifying them on the fly with mass spectrometry, which is a really clever combination. And so after this wonderful pedigree, essentially Etienne came to us with a lot of expertise on how to build instrumentation, a tremendous interest in small molecules, their vibrational properties, as well as their larger 3D conformations. And the idea that we wanted really to apply this expertise to some meaningful system. And you see the depth of his work in his years in Wisconsin, where he's been able to build his own equipment, essentially including both mass spectrometry and clever ways to cryogenically cool molecules similar to what he had learned with the Mark Johnson lab, and analyze their properties in detail, but apply this to a very important problem, which is that of reaction dynamics. And so you all know from your undergraduate courses that there is no way that you can really ever prove a mechanism of a chemical reaction. And this is perhaps still true today, except that when you go in as much detail as Etienne does, you'll see that you'll be able to characterize and isolate intermediates that are so evanescent and so transient that basically there's no other way that you could possibly learn about them in other ways. So we're really getting closer and closer to actually determining reaction mechanisms in this work. Etienne has got a lot of awards for his wonderful work, including the NSF Career Award. He's a Sloan Fellow. He's been receiving an award from the Department of Energy, and also the American Society of Mass Spectrometry has given him a Researcher Young Investigator Award recently. Etienne has participated to the life of our department, of course, in many other ways. He's been teaching several classes, both at the basic undergraduate level, especially Chemistry 109. He has taught quantum chemistry to undergrads, 562, and he's also taught reaction dynamics, a graduate course, 762, that I'm sure some of you have actually taken. He has also been teaching these classes in a very good way, but he has also been an innovator. And some of you that may have been PAs for Etienne may know that he has basically banned the use of blackboards altogether. And he walks around the classroom with his little laptop writing on an electronic pen, so that students, even those that are a little bit short-sighted or they have problems, even from the very end of these gigantic classrooms that we sometimes teach into, can really read very well. And this idea to really sharing this electronic way of writing notes is something that we are probably all going to attend to eventually, but really Etienne is the pioneer of this new way of teaching. And so without further ado, I am going to leave the floor to Etienne, but first I want to say a couple of quick things. First of all, postdoc, graduate students, undergrads, if any, you can meet Etienne today at 1 p.m. in UW-305F, which is the TCI conference room. If you think that there are still questions you're not clear about, if you want to learn from Etienne not only about the science, but also how he decided to become a professor, how easy or hard it was to be here at UW-Madison, anything you want to ask him. We're really trying to encourage you students and postdocs to talk to our young faculty more. So please consider attending this meeting with Etienne. And also if you want to learn even more and maybe visit the labs, all you need to know is to go to the 4th floor and look for the big G with the hair, which has become a logo for Etienne's group, and it was essentially created by Erin Duffy.
Thank you. So let's see if I can figure out the light here. Okay, so, and I'm gonna, if volume is a little high, maybe. Is that okay? Everybody can hear me? Perfect. So thank you all for coming to hear what I have to say, what I did since I started here in 2012. I have the very difficult task to go right after Randy. So the only way I can top that is if my computer crashed twice. So I came fully prepared, okay, for that if that were to happen. Okay, so. As Sylvia alluded, I'm interested in sort of getting a molecular picture of reaction dynamics, okay? When you think about chemical reaction or dynamics, there's several ways you can get at it. And the most popular way, I would say, is to try to follow the reaction in time, right? Try to do dynamic, try to see where things are going in time, okay? I've always been favoring sort of the other side, which is to try to look in sort of the frequency domain, okay? Try to get information about the potential energy surfaces themselves rather than trying to figure out what these are from the dynamic, okay? And that's sort of a personal way, right? I think it's easier if you have the potential energy surface to understand the dynamic than understand the potential energy surface if you have the dynamic, the other way around, okay? And so, so I always been interested in using spectroscopy in frequency domain to learn about potential energy surfaces in the context of chemical reaction dynamic, okay? And when I was a graduate student, I did that for very simple reaction, okay? Chlorine plus H2. And you can really sort of understand, the finer detail here of a reaction like this. But okay, we're in 2018, if you talk about chlorine plus H2, okay, everybody sort of rolled their eyes, okay? So you need to be looking at really, reaction of the scale of what people use in the real beaker, in the real flask, okay? You need to understand something like this. If you want to do that with spectroscopy, you really have to use a reductionist approach, right? You have to sort of take a big complicated problem and be able to parse it in small pieces, okay, that you're going to be able to manage. The challenge for us is to have those small pieces with all the complexity that we need to be able to relate directly to something that is real, right? That's really, as you see during my talk, the challenge of what you're trying to do. But I think, I like to think in molecule like this, right? Balls and sticks, and try to understand, okay, from that potential energy surfaces, how that relates to mechanism, and then you go back and now you can understand how can you, do the reaction differently, have different catalysts, have different way of controlling solvents and so on to change the reaction dynamics. That's really what we're trying to do here. So, okay, you want to isolate interesting species to be able to study them. There's different way of doing that. Our favorite way is to use mass spectrometry, okay? And we use a lot of electrospray ionization, which is a very nice way to go from a solution to an isolated species, an isolated ions, okay? And so you can easily bring that into a mass spectrometer. And now there's several interesting things about being in a mass spectrometer, okay? The first one is that you can really control the environment. Well, you're in a vacuum, but you can bring gas if you want, right? You can really control things, and you can easily move these particles around. They're charged, they're ions, okay? All you have to do is flip a voltage. You can push them away, right? So that's really good if you're trying to do things, manipulate stuff. That's really easy. The problem is, right, a mass spectrometer, well, it gives you a mass, okay? And there's a lot of experiment you can do to get hint about structure, but really it's difficult to get a precise structural information about something in a mass spectrometer, okay? You would really want to be able to do spectroscopy in addition to just getting the mass in order to characterize the structure, okay? That's quite a challenge. And the reason is, right, the numbers are really against you. So in a typical mass spectrometer experiment, at any given time, you would get about 10,000 ions, okay? Give or take an order of magnitude, okay? But the problem is those particles are charged, and there's nothing in between, right, to shield those charges repulsing each other, okay? So you cannot sort of have a very dense sample, okay? Because everybody sort of repeat each other. So the highest density you can hope for is about 10 to the 6 ion per centimeter cube, okay? It's hard to imagine what that represents. So I tried to find an actual picture, okay? And so the best I could find is some fancy physics experiment, okay? Those little dots are individual ions in an ion trap, okay? So there's a potential sort of pushing them together, and then they've been laser cooled to, micro-Kelvin temperature, okay? So slow that you can actually measure the fluorescence from them, and they're always in the same spot. So you see these little dots, okay? And so the distance between each ion here is about 20 microns. That's a very best case scenario, okay? That's 0 Kelvin. And if you calculate it, this is 10 to the 8 ion per centimeter cubes, okay? So remove 99 ions here, that's what we have, okay? There's not even 100 in that picture, but I think you can do that, okay? So this is the kind of density. In chemistry term, what we have, our sample size is 10 microliter of a 1 femtomolar solution, okay? This is what we have. So we want to do spectroscopy on that. So, of course, we cannot do direct absorption, okay? So that would be the typical way of doing spectroscopy. You would look at photon. You put 10 to the 15 photon in, and you look how many of them are across your sample and are the other side, okay? I tell you, ion density is low. There's nothing you can do about it, okay? Cross-section for vibrational spectroscopy is not very high. Nothing you can do about it. You can try to make your length very long, but you're going to have, several kilometers before you get, anywhere close to where you could actually make that ratio not being 1, okay? And so you cannot look at this by looking at the photon themselves, okay? We're several order of magnitude from what you can do with cavity ring down, for example. So you can take your Beer's law and you can flip it around, okay? And now you can look at ion instead, okay? So N0 will be total number of ions. N(V) will be, well, how many of them did not absorb a photon after all of those photons passed through, okay? And now this depends on photon flux, okay? And that, I can build a big laser, and I can make that number big, okay? And if I make that number big enough, this is going to be a reasonable fraction, okay? 90%, 80%, something like that, something that I can actually measure. So in a mass spectrometer, okay, we can actually do that with incredible precision. I can measure a single ion, okay? I can count ion very easily. And so all I have to do is find something in which the actual absorption of a photon will give me a measurable action, right? In a mass spectrometer, it has to be a change in mass, right? If the mass is different, then I will be able to figure that out. Okay, this is called, it's a very general way of calling that action spectroscopy. You're looking at the action induced by the photon rather than the absorption itself. Okay? I didn't invent any of that. People have been doing that for quite some time now. There's different way, different scheme of doing that. Most popular one is you just pump a ton of infrared photon until you actually break a covalent bond. Okay? And so this is kind of a tough process because you're resonant with one vibration. Your infrared photon is not a lot of energy. You need to wait until that energy dissipates into other mode to pump another one, and so on, until you reach a big dissociation threshold and you break your molecule apart, and now you measure that change of mass as a function of your laser wavelength. Okay? And so that will work with anything, any molecule, but you're going to need a really, really big laser to do that, okay? Because you're going to need 30 photon, something like that, to break a covalent bond, okay? And so there are 3 of those lasers in the world, okay? They are about 25 million a pop. I've been to one of them when I was a grad student. One of them is in Netherlands. It's also a nice thing to spend a few weeks in Amsterdam as a grad student. Okay, you can do these nice experiments. Works very well. Obviously, I'm not going to have that in my lab here, okay? Another way, if you want to do that in the comfort of your own lab, is to replace all of these photons by one UV photon, okay? A lot more energy. So if you have a suitable chromophore, a UV photon is enough to induce a dissociation, right? Photofragmentation in the UV, okay? Pretty common. And so then you can play trick by doing, for example, ground state depletion with the infrared, and you look at the change and so on, and you can actually do spectroscopy now with 2 lasers, one infrared, one UV, okay? You can do that in your own lab, but you need a molecule that has a UV chromophore, okay? Usually a phenyl group, phenylalanine, something like that. That will work perfectly well. If you don't have that, well, that's it. You can't do anything, okay? So the third way, my favorite way, is to actually make a bond that will be artificially very weak. So weak that a single infrared photon will be enough to break it, okay? And the way to do that is to attach something very weakly bound, like, for example, a rare gas, like an argon atom. You can imagine at very low temperature, that argon is just physisorbent to your molecule, okay? It's a very weak interaction. One infrared photon, that's enough to put you above the dissociation threshold, and all you look is for the loss of that rare gas, okay? You can do that with one laser, okay? And if you're able to form this, you can do that with any molecule, right? The challenge was, until recently, how do you make that with any kind of molecule? It was done in like supersonic expansion, which only worked for small molecules and so on. And during my postdoc, we sort of figured out the way how to do that with any ions, okay? And the way is to make your mass spectrometer very cold, okay, well, it's part of it. And so this is the instrument that we build. We have electron spray. We can bring any kind of ions, big or small. You just pass them through a whole bunch of ion guides, and we bring them into an ion trap, okay, which is attached to a big refrigerator. And so the whole assembly is at 10 Kelvin, okay? Now, the ions never touch the wall of the trap, right, because that would be the end of your ions. So if you want to cool them, you need sort of something else. So we put a little bit of buffer gas, usually helium, right? Helium collides with the wall, and it collides with ions, and it cools down your ions through several collisions like that. Not the most efficient way, right? But in a few milliseconds, you will thermalize your ion to a cryogenic temperature. Okay, and if you then add in your buffer gas, we add a little bit of D2 deuterium, okay, and that's what's going to be sort of the physisorb tag, okay, that we're going to use for our action spectroscopy. And we use hydrogen rather than argon because it works a lot better, okay, because argon condenses about 30 Kelvin, hydrogen condenses at 10 Kelvin, and so we can be at a lower temperature, so we can get a lot more efficient tagging with hydrogen than we can get with argon, Okay? So once we get our tag species, okay, not all of them will tag, so we separate them by mass. We only keep the tag one, shine the IR laser, the little, if we're resonant, the little D2 boils off, and then we monitor sort of fragment, which is just the ion itself without its tag. Okay? So if you look from the actual pilot view, okay, you would spray your favorite molecule, you get a mass. When you cool it down, you see these adduct that form, right? Those are your little D2 adduct. We will keep one of them, let's say the one that has 2 D2, okay? Shine a laser at it, and then this peak here, now you have to be careful because of the way we do this. This peak corresponds to the loss of both of these D2. Even though they appear, it's because we do that all in the same time of flight, so they have slightly different arrival timing here. But then we can just monitor this as a function of laser wavelength, right? And then you get essentially the linear infrared spectrum for that particular molecule, okay? When I go around and talk about this, I make sure that to tell everybody, like, look, we can do that, it's easy, okay? But here my students are in the audience, so I cannot say that because they know this is not easy, okay? There's a lot of work that goes into something like this because you can only do one wavelength at a time, okay? Every point here, you measure that, and then you move, you measure that, you move, okay? Quite tedious, okay? And if you want something that looks good like this, it's gonna take you several hours, maybe a day, okay, to get one spectrum, okay? And so not as easy as just press F5, you know, and get your spectrum, okay? And so we'll talk a little bit later on why that is and what we can do about that. But this is what we have right now. The other thing I want to point out is that because we're cold, okay, we can actually go further than just functional group spectroscopy with infrared, right? If you're familiar with you know, the usual FTIR, there are a couple of blob, you know, one of them is CO, one of them is the OH, and that's pretty much it, okay? But here, you know, if you look at this big thing, there are 10 OHs, and if you look in the OH region, okay, you can make out almost 8 different peaks. Every one of them in a different chemical environment is giving you a different frequency, right? This is the kind of information we can get with that spectroscopy, okay? A lot better than just saying there are OHs or there are no OHs, okay? The other way, for example, here we look at the CO frequency as a function of a ligand on the metal. You can see a subtle shift in splittings and so on, so we can get information even about electronic structure in these type of complex by analyzing the kind of spectrum that we get here, okay? Okay, so I'm gonna try to tell you 3 stories, okay? But they're all part of the same story-ish. You know, this is typical tenure talk, where you have to talk about everything you did and try to squeeze everything in. Okay, so I'm going to try to do that. And the first I'm going to talk is our work on looking at intermediate in catalysis. Okay, a lot of our work, we've worked on water oxidation by this ruthenium complex here, and I put you the proposed mechanism for that. Now, our role here is not really to make a better catalyst, like synthesize something. We want to try here to understand, well, does this make sense or not? But also, from my point of view, a lot of the important thing here is that this is a multi-step process. And so you can think of as your intermediate at every step as being the catalyst for the next step, right? So you sort of have to understand the reactivity of an intermediate in order to be able to predict, you know, what would be the barrier for the next step, if you would, okay? And so, and how you can, for example, change the structure of the initial thing to get the right thing, you know, and so on. So that's one thing we want to do. The other thing is we want to know how does the role of the solvent, right, in these reactions here. You're removing electron and proton, so of course solvent is playing a big role, and you want to know. Those are metal center species, you know, that are, you can use DFT to describe that. You want to know, is that a good thing to do or not, right? Can you really describe these species with the DFT, for example, which is used widely to help sort of formulate these kind of mechanisms. Okay, so if we want to get these species, we have to sort of get the reaction going somehow. Okay, so our first try at that is to try to form them electrochemically in solution right before the electrospray step, okay? So we put our catalysts in solution, we flow them through an electrochemical cell, and then we try to sample what's happening here as close as possible to the electrode, okay, with the electrospray. And so doing that, okay, if you just look at the mass spec itself, at 0 volt, you get a whole bunch of peaks, but that's one species. Ruthenium has 11 stable isotope, okay? And if you crank the voltage a little bit, okay, there's a species appearing that corresponds to the loss of one hydrogen atom. 1.2, another one, another loss of hydrogen atom, or one electron, one proton, if you would. And all the way to 2 volt, in which we look very hard everywhere, and we haven't been able to find any other species than these 3, essentially, okay? And we know we're at a voltage where we essentially, you know, the whole thing should be going through, right, above sort of the threshold to actually form oxygen. So we're not quite sure why we don't see these other species, but the most, you know, there's several possibilities, but the most probable one is that once we pass sort of the bottleneck of the reaction, the other steps are probably extremely fast because the potential for that is much lower than the potential that you are. And so those species probably never leave the actual electrode and just cycle through very rapidly, okay? And so we haven't been able to isolate them using this method. But we've been able to characterize sort of the first few that we've seen, and you know, I'm making sort of a short story, but we look, for example, at the actual bonding between the ruthenium and the hydroxide, using sort of a calibrated scale for the polarity of that bond versus the frequency of that bond. And the bottom line is that, you know, formally you would describe this as a ruthenium-3 hydroxide, but it's much closer to sort of a neutral hydroxyl to a ruthenium, if you would. So this thing is actually acting a lot more like a regular alcohol than, for example, an hydroxide ions. So, of course, there's other interesting species in the cycle that we cannot get from solution. So, in particular, we were very interested in the last species here, the ruthenium O2. Okay, and the reason why we wanted to get there, this is the last species in the cycle, and the substitution of the O2, your product, with the next reactant, the water, is actually very slow. Okay, in solution, if you use chemical oxidizer, you know, for equivalent, you really get stuck here. That step is the rate limiting step. Okay, and so so that's interesting. That means that your catalyst is binding to the product a little too strongly, right? And so, but if you use theory, if you use DFT, and there's been several studies on that, it's telling you that there shouldn't be any significant barrier. That should happen very fast in solution, okay? And so we were very intrigued by that, so we wanted to get to that species. So the electronic structure of this is quite interesting. You can bind side-on, end-on. There's triplets and singlets and so on. So it's obviously not a simple species here. So how do we get there? So we cannot get there from solution, so, well, let's try to get there from the gas phase, okay? So what we did is we added a new ion trap to our machine, okay? Because our main trap, we're stuck at being at 10 Kelvin if you want to do the tagging, attach that little D2, okay? And only really happens at 10 Kelvin. At 10 Kelvin, you can put helium and you can put hydrogen. That's it, right? Any other gas, just stick to the wall, and that's the end of it. So we added another one with the hope that we have more flexibility and be able to manipulate the ion before we do the little tagging step, if you would, sort of a preparation step, okay? And so using that, we did our sort of, you know, first total synthesis in the gas phase, okay? We started with our precursor ions, okay? You spray that, that's the mass you get. In the high pressure region, we activated. That's the nice thing about ions. Okay, you want to warm them up, you crank up a voltage, they just run into the gas a little harder, they warm up. Okay, you can create this very reactive species that has lost the water ligand now. Okay, of course in solution, you know, there will be another water coming right up. But here, we're in a vacuum. okay? There's nothing coming back up. In fact, there's some residual gas, and if you just leave that for a little bit, it will pick up actually a residual nitrogen from the background gas, okay? That's a pretty reactive thing. But if we bring in our reaction trap, and at 80 Kelvin, we just put some oxygen in there, we can very cleanly actually synthesize the intermediate that we wanted to study, okay? So that's the kind of control. We can get two things here that are important, okay? We do need to activate it for it to react, okay? If you just have the water and you put oxygen, nothing happens. The trap needs to be at 80 Kelvin, as cool as you can, in order to see that product. At room temperature, you form very little of this, okay? Which for us was like saying, looks like this binding is extremely weak, okay? Which would be correct with theory, but completely different than the experiment in solution, okay? And so we characterize that species with the spectroscopy. This is in the fingerprint region. We're looking for that oxygen-oxygen stretch, okay, which is going to be characteristic of the binding motif and in spin state. Hard to tell which peak of that is O2, right? They don't come pre-labeled. So we use isotope, right? Oxygen 18 that we stole from an empty bottle in John Berry's lab. Okay, that was still enough for us. And then you can see this little tiny peak here disappears. It moves about 60 wave number, okay, which is exactly what it should for the mass difference and so on. So this is our oxygen-oxygen stretch, okay? And now we go to the computer, and we put in all of these different structure, and while none of them actually gets the right oxygen-oxygen frequency, okay? That means that DFT here is not describing these species properly, okay? Not too surprising because, you know, spin states and metal and DFT is notorious for being bad. And plus here, O2 actually itself is notorious for not being, you know, describable by a single reference method. There's, you know, open shell character in a singlet state, and that same thing is happening here, okay? And so, but we're spectroscopists, and so we say this is what we have, because that OO stretch is perpendicular to the axis of symmetry. Okay, if you remember your PChem class, that means it's going to have almost zero dipole when it vibrates, right? That will be a very weak infrared transition, and this is what we're seeing. All the other one would have a very strong oxygen-oxygen stretch, right? That would be quite obvious that we don't have that. So if we trust that this only happened on the singlet surface, you know, we're thinking we have a singlet side-on molecule, okay? How does that then compare with everything else, okay? So this is what theory is telling us that we had, and we're pretty sure that it's not the case, okay? What we think we have is something closer to that. Now, I don't know the actual binding energy. I don't have a way to measure that, but I know that because in my trap, I'm coming on the triplet, right? I'm coming with a triplet oxygen. So I'm coming on a triplet surface. This, we know, is very weakly bound, right? That's why you need to be cold, otherwise it gets destroyed very easily. But this is not what we observe at the end, which means that it needs to be able to cross to the singlet surface, right, and find the minimum, right, which is going to be the singlet side-on. So that means that the crossing point, right, should be pretty close here to where the triplet species is, so that you cool it down, have enough time to cross, and then it finds a singlet surface.
Could you give me an idea of the scale and the y-axis?
No. and you know, and that's the thing when you just have the spectroscopy, right? I don't have that energy, right? Calculations tell you it tens of kilojoules, you know, 10 to 40 kilojoule per mole. But really, I don't know how much I can trust any of that. And there are ways to measure binding energy, and we haven't got to do that, but we could get that information eventually. But so I think this is what's happening, and that would explain why this is slow. Because in the catalysis, if you form this, you have to go all the way up to that crossing right, to release the oxygen. And that's the rate limiting step. Okay, you have to find that minimum energy crossing to cross back to the triplet to exchange with the water. Okay, and that is what is slowing down the reaction here, which is actually, you know, something that usually people don't think about too much when they see something like that. But when you're removing and adding electron, right, you have to really be careful because all these spin states become accessible. Okay, so so this is our story with the ruthenium. But the nice thing here is that we sort of learn how to get to a species that we want, right, by having enough control to do the chemistry, if you would, in a way that is slightly different than you would in solution. The next step that we wanted to do, right, now that we have this reaction trap, okay, is to bring the solvent back into the picture. Of course, the solvent is playing a huge role in this kind of reaction here. And if you put your ions with some water at 80 Kelvin in the reaction trap, you start forming these very nice water cluster. Okay, you're clustering water onto these ions. Okay, and as a personal note, okay, this is something that I've been trying to do for way longer than you think. You know, I've been trying to do that. Okay, it's been 10 years of my life spent on doing that. Okay, so when we actually did something like that in the lab, and it was actually simple, right? I remember just sitting there like, why did I do that before, right? But this is really cool because you can bring, you know, this is the thing, right? In the gas phase, you don't have a solvent, and everybody's like, you don't have a solvent. Well, you can bring it, but you can bring it in a way that you can start understanding the actual role because you bring in one molecule at a time. You can still get a molecular picture of solvation, if you would. Okay? And so we can do that with pretty much any molecule. And I'm showing you here, you know, an intermediate like the hydroxide. We can start following that OH frequency as a function of solvation. I'm not going to get into structure here, but I'm going to tell you the kind of information you can get from this spectrum, apart from structure, is that the shift you're seeing here, okay, this delta nu, is actually related to the strength of the hydrogen bonding interaction that's causing it. Okay? This is an empirical relationship, but you can really get a pretty accurate estimate of the hydrogen bond strength, an individual hydrogen bond strength within sort of a whole network, right, of hydrogen bond. And that's pretty difficult to do by any means, okay? And so this is sort of the way that we try to approach these kind of spectrum, is to decompose now these hydrogen bonding interaction into individual hydrogen bonding interaction, okay? And so briefly here, I just want to, for example, compare the hydrogen bonding network around the initial catalyst with the water and the first intermediate, the hydroxide. Okay? The reason is that, you know, it's all PCET, right? If you're removing that proton at the same time you're removing the electron, usually the barrier for that is the solvent reorganization. So you want to be able to look at what the solvent looks like before and after. I cannot look at what it is in the metal, but I can look at before and after. Okay? And so with the water, if you just add one water, you get a huge shift in frequency. Okay? It's telling you that this water is actually forming extremely strong hydrogen bond. That means essentially that this water is a lot more acidic, right, than a regular water. And that's the catalyst doing its job of making that more acidic. Okay? On the other hand, the hydroxide, a very small, very usual shift, and essentially this is acting just like a regular alcohol. It is not activated much by the metal. Okay? But if you keep adding water, here you start forming sort of a double hydrogen bond, right? And so you don't get any more shift. So adding more water does not give you a stronger hydrogen bond because there's a strong anti-cooperative effect. As you bind to the other OH, okay, you form another hydrogen bond, but you're weakening the other one, okay? And overall, they just exactly compensate each other. Not the case here with the hydroxide. You keep adding water, all these water, tug a little more, right, and keep increasing the strength because that anti-cooperative effect is not really strong in there. But the bottom line is if you look here, there's like 4 or 5 water. this and that, okay, roughly look the same. Okay? In other words, before and after removing that proton and that electron, the water network around the active site looks exactly the same. Similar interaction strength, right? Similar structure, and so on. So in other words, you're sort of in a best case scenario where your two wells are pretty much the same, and that's why you're going to get a pretty low, solvent reorganization barrier for that process. Okay? Obviously, we would like to have a lot more water than 4 or 5. Okay? And we can make those. I'll show you the mass spec. Okay? But you can see already, I'm starting to lose, right, the nice sort of well-resolved spectrum, right, that I love. And it's getting crowded, it's getting broad. And very, very quickly, you lose that ability to just connect a spectrum with a molecular picture, okay? And now everything we do, pretty much useless if we cannot do that, okay? And so when we hit that wall many times, and clearly, we had to sort of like, oh, okay, we need to do something about this if we want to get to a more complex system. And so it can be two things here. First, it could be that there's several isomer or conformer, right? They all have the same mass. I cannot separate it in mass spectrum. And they all have slightly different spectrum. They all overlap, and that's creating a lot of congestion, right? That's one possibility. The other possibility is just that there's too many peaks too close to each other, and it's just spectrally getting very congested quickly. Okay? So there's these two possibilities. And so the next two stories are going to be, how do we deal with something like that? Okay? So I'm going to switch kind of system to show that, so I can show you more stuff that we've done, right? So the first one is how to deal with isomer complexity looking at glucose. Okay, so glycan in general, of course, are very important in biology. They're very challenging for mass spectrometry because you are trying to differentiate between stereoisomer, right? Difference between galactose and glucose is the stereochemistry of one OH group. A mass spectrometer will not really give you that. They fragment the same way, they react the same ways, and so on. Right? And then when you start linking them together, there's alpha, beta on the linker. It can link in different positions and so on. So again, a lot of isomeric complexity, which a regular mass spectrometer it's very hard to differentiate. Okay, so there's a lot of ideas around in the community to try to deal with glycans and sugar in general. And this paper came last year, okay, where it's David Klemmer and Tom Rizzo. So they used first ion mobility. Ion mobility is chromatography in a mass spectrometer. Okay, big molecule collide with gas, they slow down. Small molecules, they go faster. Okay, so you measure a drift time. They pretty much all have the same drift time, right? The shape, the structure doesn't change too much. On the other hand, if you take the infrared, and so they took those spectrum with the exact same method, okay, that we're using, although ours look much better than theirs, but that's for me, okay? But you can see how characteristic the IR is of all of these isomers, okay? They're really, really different. Even if you have conformer here, ion mobilities separate two conformer. They're the same molecule, but they're folded in a different way or something. Okay, very different infrared spectrum. Okay, so there's something here in where maybe a spectroscopy, right, can be helpful in cases like that. So we wanted to dig a little deeper here. They didn't assign anything. Okay, they just published a bunch of spectrum, and so we wanted to see. Can we separate all of these isomer, conformer, and so on just with the infrared spectroscopy, right? What if you have a mixture of these things? Can you separate them in the spectrum? So we started real simple. Okay, glucose, you get an alpha and a beta. You put them in solution, right? They equilibrate, and you can get both. We take an IR. It looks fairly simple, but if you zoom in, there's a lot of peak there, okay? There's a lot more than 2 species, okay? That means that they are the 2 alpha and beta, but they are conformer, okay? And the reason is that we're adding a sodium. Sodium can be in different places and so on. Okay, so how do we separate these things just with spectroscopy, right? If one laser cannot do it, well, then you put 2 lasers, okay? So we put 2 lasers. So here we have the probe laser. That's the laser we've been using, okay, in a time of flight, same as usual. And a new one, pump laser, in the ion trap, okay? So 2 ways to do this experiment. First, you fix the pump laser to a particular transition in the ion trap. It will burn, literally burn, all of the conformer giving rise to that peak, remove their D2, they have the pool of molecule that the probe laser is going to be probing, okay? So you get a different spectrum. You can see we can remove 100% population. And then you can subtract these two, and this is the spectrum associated with that particular peak feature, okay? Or you can do it the other way around. You can fix the probe laser to a particular transition. That means I'm going to be continuously forming fragment. And then I scan the pump. And when the pump hit a peak that belongs to the same conformer, it's depleting it. My signal is going to deplete. There's a dip. Okay? So you get a dip spectrum. That's why I put it the other way around. This is literally a dip spectrum as you scan the pump laser. They give you exactly the same spectrum. They have their pros and their cons, okay? I'm not going to go into the detail. We use whichever works best for us at the moment, okay? Most of the time, we try to use the dip method. So we went and dipped all of these peaks in the glucose. I'm showing you a few of them here. But I prefer to show you something like this, okay? Disclaimer, there's a lot of cheating involved in this figure, okay? That's why it's not in the paper, it's just between us here. Because I didn't took every single pixel, data for every single pixel in there, right? I took a couple of lines in here, a whole bunch, okay? But not every single pixel. But you can read this, okay? This is a 2D correlation map with the 2 lasers, okay? So you can look at this peak and this one, they have a cross peak, which means there is one conformer that shares these 2 features. This guy and this guy, no cross peak. There's no conformer sharing these 2 features, okay? So you can go along and play the correlation game, okay? And you can extract the actual infrared spectrum of 8 different conformer from something like this, okay? Each individual conformer gives you a spectrum. So I'm not going to show you all 8, but I'm going to show you 2 of them, alpha and beta with the sodium in the exact same position, just to show you can very easily sort of differentiate between these 2, right, using the spectroscopy. They give you a very different signature in DOH because these 2 guys are in a different environment than in the alpha conformation, okay? So we can indeed separate a sort of subtle stereoisomer like this using only infrared spectroscopy. So this is all 8 of them stacked together. They all stack to the overall spectrum, so we know we're not missing anybody here. And essentially, if you bin all of them in alpha and beta, we get pretty close to the actual solution ratio, right? This is within our error bar for determination of these kind of things. So we know we can actually determine solution phase ratio of alpha and beta. Okay, so this is all using 2 laser experiment. We can separate very complicated conformal isomer structure. Okay, the very last thing here is how do you deal with spectral congestion? Okay, and that's another project we just started looking at salvation of peptide. Okay, I show you we can form these water cluster. It can get a lot bigger than that, 30, 40 water around a peptide. And that's very interesting because the structure of these kind of objects, of course, is completely determined by the solvation environment, right? The competition between hydrogen bond with the water, with itself, hydrophobic effects, and so on. The acid-base behavior of those things is really modulated by solvations and so on. So we want to be able to decompose all of these effects into sort of molecular effect, if you would. And here we can actually make these objects, okay? The thing is, it gets annoying very quickly, okay? If you just look at just a simple, triglycine with 1 watt. This is a triglycine itself. It's very congested, but that was 2 different conformers that we separated with our 2 laser, okay? Weird thing happens. Your protonation site is not where you would normally put it, okay? That's what happened when there's no water. You also have very weird amide conformation happening, okay? And so very weird structural thing happened without any solvent. If you had only 1 water, the spectrum changed completely, which is very exciting because it's telling you 1 water is doing a lot of things here. But there's way too many peaks, and so we went and tried to do our 2 laser experiment, and well, came out negative. There's only 1 species here, but way too many peaks. And this is a case, you know, that we all dread, which is when our double harmonic approximation, right, is not valid anymore. And then, since we rely a lot on computation, these cases are very difficult for us. Not very complicated molecule. But already, you know, we have to hit the brake, okay? And so the reason why it's hard is that the mode of the water, right, bending mode and stretching mode, they overlap with all the important mode of the peptide itself. Amide 1 and 2 over here, NH, OH of the peptide itself. They are in the exact same spectral region. That's why in solution, if you try to do IR of biomolecule in solution, right, you will never be able to look in this region. That's water, right? And so people use D2O, okay, so that they will shift the bending mode away. CO won't change even if you deuterate the peptide, and then you have a chance of looking at the CO in solution, right? But we would really like to sort of look in there too. There's a lot of information in there, okay? But we are not in solution. We are in the gas phase, so we can do whatever we want, okay? If we want to stop the exchange, HD exchange, we can just stop it, okay? So this is our favorite peptide, sprayed out of a solution in regular methanol, so there's hydrogen everywhere. And we put it in contact with D2O in the reaction trap at room temperature, right? And that's, in the mass spectrum, you can see the exchange of hydrogen with deuterium. It had 1 mass, so this is happening, right? This is normal. If you cool it down to 80 Kelvin, you can completely quench that, okay, that exchange. It doesn't happen. And all you're doing now, you have the all-H peptide, and you're adding a D2O on top of it, right? So you're doing that experiment that you cannot do in solution here, which is to separate the spectral signature of the solvent from the analyte itself, okay? And so if you do something like that, this is very recent actually, and this is simple glycine with a few water, okay? This is the spectrum you get if you add water, the spectrum if you have D2O, okay? I'm showing it in a weird way because, okay, if you just put them on top of each other, okay, no trickery here. Purple, all right, red plus blue. Purple is the same whether you have H2O or D2O. That's your peptide, okay? Red only happens when D2O, that's your OD of the solvent. Blue is the OH of the water, okay? And so it doesn't matter how many water I have around it. I can always sort of separate their spectral signature. I can have as many water as I want around a peptide, and the spectrum is not going to get more complicated, okay? It's always going to be the same. And so that will enable you, I think, to really expand sort of the scope of what we can do in terms of size and in complexity. And so we're really excited about this. If you do a whole bunch of them, you can sort of just follow the purple, okay? Forget about everything else, and you can see how these form a strong hydrogen bond when you first do a cup of water, and it comes back up, but it's already starting to converge pretty quickly, right? And so we're going to be able to sort of look at these kind of things. If you squint very hard, there's small differences because, well, a deuterium and a hydrogen, it's not the same thing quantum mechanically, okay? 0-point energy. Here you have 2 different conformers. The energy get different, you get different population, and so on. So there's all kind of interesting stuff coming out of these experiments. This is very recent, but we're really, really excited about that. Okay, now what? Okay, so we reached today. Okay, and so as Randy said, when you come here, you come with a dream, a prayer, and a small loan of $1 million. Okay. It is really a loan, okay? You spend the rest of your life reimbursing that loan. 50% of every grant you're ever going to get goes to reimburse that loan, okay? So not a gift at all. Okay. So what do you do now? Okay, of course, money evaporates quickly, okay? And your dream gets squashed quite a bit by reality, okay? And so what do you do? Well, I'm not going to get another loan, but I can get new dreams, okay? So that's free, okay? Thank God. So here's two dreams, okay? The first one, it started as a joke, okay? I was giving a talk. I was preparing my talk in my hotel room the day before, and I need a joke. So I was presenting our work with the dual trap for the first time. So I said, I'm going to finish by saying we're going to put a whole bunch of these traps. And so I put 4 of them because the acronym spells quitters, so I kind of like that. And then the thing is, if you ever give scientific talks, okay, you're going to realize when you make a joke, there's always 10% of the audience who's not going to get it, right? And some smart ass is going to ask you, what are we going to do with 4 traps? So I was like sitting in the hotel room, right? Like, what am I going to do with 4 traps, okay? And by the end of the night, I was convinced that we really needed to build those. Okay? It's like, oh yeah, no, we really. So what are you going to do? Okay, let's say you want to look at interfacial water between biomolecule and the solvent. Well, you just make it D2O, you put H2O on top of it in the second trap, right? Spectrally, you're only looking at one thing, the thing you want. Okay? You want the second shell, well, you put water, D2O, and another shell in the third trap. You're only looking at a particular position. You're decomposing that complicated thing into like tiny bits that make sense. Okay? If you want to do, I don't know, surface chemistry, put surfactant, whatever, you can do it. If you're going to do fragmentations and so on. So the basis, the thing that came out to me, right, was cluster synthesis, because the idea is exactly the same as organic synthesis, right? If you want to synthesize something, you're not putting everything in the flask at once and just like, is it going to happen or not? It never happens that way, right? So this is exactly what we need to do, okay? We need to do one step at a time, cleanly, control condition, clean up our mess. That, for us, it will be mass selection, well, and then go for the next step, and so on and so on. And then we'll be able to build things in a coherent way, right? That will be much easier for us. So I came back, and my students know I've been annoying about that because I think it's exciting, and so we're going to do it. The shop is working on those right now, so that dream is going to happen. I don't know if it's going to work, but we'll try it. Okay? Dream number 2. Dream number 2 is that, well, I'm getting a little tired of waiting, for my student to, give me a result, right? But this is a hard experiment. I know it takes a lot of time. But if we were a lot faster and if it was a lot simpler, this would be a much more powerful technology, okay? Because honestly, it would be a lot more powerful if it was, if I could put it in somebody else's hand, right? Somebody who know what they're doing, okay? And so, for that, it has to be simple and it has to be faster, much faster. Nobody is going to sit around for a day, okay? And so if it was fast, you can say, for example, let's say you have liquid chromatography, right? Right now you're doing LC-MS or maybe MS-MS on that, right? Imagine you can take an IR of your peaks of fragment in addition to the mass, right? And so if you're trying to figure out the structure of a brand new molecule, a metabolite of a drug, or your enzyme is producing something new, you don't know what it is. Isolating, sort of large quantity of unknown is really the rate-limiting step in identifying the structure of new molecule. So what if you can get all that information just with an LC-MS IR, okay? And so I think that would be very powerful, but how much time do we have to do that? Well, half a minute, 20 seconds, right? This is 2 or 3 orders of magnitude faster than our current rate, okay? So we need to get better. And so we're trying it. We're playing with, do I know how to do that? Not quite, but we have a couple of crazy ideas. But in particular, I'm very excited about sort of new laser technology. because most of the rate limiting step in what we're doing is our old 10 Hertz laser, right? But we need a lot of photon, right? That's hard to do at a higher rep rate. Quantum cascade lasers are getting there. They're getting to a regime where it's going to be very interesting for us. And those are sort of quasi-continuous. You can modulate them at megahertz frequency. You can scan these things at an incredibly fast rate, right? So if you want a fighting chance, something like that, learning how to integrate something like that into our sort of workflow will be really key, okay? And also, if I know that I can take a spectrum, right, in 10 seconds, that means that my signal to noise will be good enough that, well, for the next, in 10 years, I'm going to have to be able to have new dreams, right? I'm going to be able to dream about other kind of spectroscopy, which will be harder than what we do, right? Circular dichroism, or nonlinear spectroscopy, Raman, 2D IR, something like that, right, in which the signal is much smaller. But if I can do my little tiny linear spectroscopy in 10 seconds, I'm allowed to dream about new spectroscopy, okay? So that will be the goal for I don't know, in 10 years or something like that. So I'm going to wrap this up, I'm a little over time, by thanking everybody who helped me, and I cannot put everybody's name on here, of course, but all the staff, both admin and teaching staff, right, actually make this place run, because it's not me. Thank you for all the work that you do. Special thanks to the shop, right, that build all of our fancy, all of my crazy idea that I get while in my underwear in hotel room, okay? Comes to as long as it's made of metal or plastic, it can come to reality, okay? The shop has built tremendous stuff for us. Thanks to Jeff for giving us, nice lab and everything. Thank you to my mentoring committee, Marty, Gail, Clark, and Mark, for all the advice and support throughout these years. I'm going to add Fleming on top of that, even though the first thing he did when I arrived is to just skip town for 5 years. But thank you for all the advice and everything. Thank you for the lab space and office space so that we can actually stretch our leg a little bit. Really appreciated that. Thank you to the actual folks that did the real work, okay? So these are my first two students, Brett and Aaron, okay, that started. It's always scary to start in a new lab, right? But in an experimental PChem lab, you're really starting far away, right? When everything you need doesn't exist, okay? And that's how these two started, absolutely nothing. And that's a Home Depot bag. I think I probably brought some garbage from Home Depot. And really got our lab up and running quickly and did fantastic work. Brett is now doing a postdoc in Berkeley and actually managed to get a faculty offer before I even get tenure, okay? I don't know why it's been possible. Aaron did a lot of the work with the ruthenium and a lot of the doodles and drawing and all that we still use, like our official logos and so on. And then the group sort of grew from there. You can see it's getting brighter and brighter around us as times go. So we have to wear goggles now all the time. So thank you to John, Steve, Glenn, Caitlin, Casey, Cole, and Summer for all the work, for being awesome people so that I don't have to be an asshole professor or anything like that. You guys are making it very easy, okay? And, well, special thanks to Gia, okay? Everybody always here and can imagine how awful it is to share your life with a professor, right? But imagine that Gia's, spending not only time at home, but time here with me, working on stuff, on papers, on proposals, and whatnot. So that's been incredibly helpful. And so thank you for everything and all the supports and so on. And these people, help me reimburse that small loan of $1 million. And I'll stop here, and thank you all for your attention.
a couple questions. One is, what is determining the intrinsic line shape in your spectrum?
The skinny one, it's essentially the line width of our laser, few wave number, and a rotational profile, another few wave number. For the big fat one, then it's a good question. Right, and this is not, you know, you've seen many of these features, especially the one that have a very strong hydrogen bond. They get broad, okay? And over again, they do that. It's not a thermal effect, right? It is a 0 Kelvin thing, okay? This is their actual line shape. There's many ways of thinking about that, and everybody has a different little idea about that. You can think, I think the simplest way is to think of just a vibrational lifetime, right? The vibrational lifetime getting shorter, and you get some homogeneous broadening, right? The mechanism for that is coupling with modes that are in the background, normally not allowed, but mix with that and start being allowed, right? That's why you don't get a very nice Lorentzian. It's not a continuous sort of distribution of mode behind it. That's sort of my, you know, and will tell you that it's 0-point motions and that kind of stuff. And I think we're all talking about the same thing in different terms.
Would it be possible in the cold trap to put something in there and then photoexcite it to create a reactive species that you could then watch?
Yes, and actually this is, well, we're going to start with the easy experiment, which doesn't involve watching in time. That is, you photoexcite and then you look sometime later and see what's left. And that we actually have you know, project to do that because of course you can start playing with all the solvent influence, all the reactivities and so on. Eventually, I think doing real dynamics in the sense we're looking at things in time would be very interesting. And I think the direction we're taking in which we're able to start from a very well-defined starting point would make these kind of experiments much easier because you're not starting from a distribution of starting point. You would start from one thing, watch it, then change it, watch it, and so on. Right? We can decompose the dynamic, I think, in a much more efficient way than is usually possible. So this is definitely on the docket, on the stuff that we want to do.
Okay, and then different question. So in the one of the challenges of the dreams that you talked about at the end, you talked about distinct H2O and E2O solvent shells. So those wouldn't mix with one another?
Remains to be seen. And I think if we're able to keep the temperature of that object as we do everything below 100 Kelvin, I think we'll be able to at least minimize that exchange very much.
If they don't intermix, then is it really solvation, or is it just a frozen shell?
Yeah, essentially, right. And that's again the two things, right. What I would be looking is a series of sort of minimum in the overall potential energy surface, right. And then again, if you want to now get information how they get from one and the other, then you're going to need something like the dynamic, in which maybe you can start with your frozen thing, and for example, an infrared photon will be enough to warm up the system above that threshold and start now the dynamic of that exchange and so on, right? And so, in a sense, I don't think we'll be able to do these experiments at temperature high enough that, yeah, things are going to start wiggle around, because then I think the exchange is going to come as soon as they start wiggling around.
But if it's ice, then, and if you want to, I mean, it seems fundamentally interesting, but if one were thinking, well, I really want to sort of learn about solvation, but then it's really not like solvation, let's say at body temperature or room temperature, if the water's frozen. Or is that?
Well, my view of it is that the potential energy surface is the same at any temperature, right? You're just populating a different part of it, right? And then the question is, at room temperature, which part is the most important one, right? Is it the part that is higher in energy, that only happens at higher temperature, or is it the part that's around where the minimums are? right? And again, we get into more philosophy of water, which is, if you get into, I go to these kind of conference and it's endless argument about these kind of things, right? And the people who have the instrument that can measure things moving around can tell you everything is about the water moving, right? And then the people who can do that but can do the other way. It's all about the same. And so I think we're talking about the same thing from different view. And I'm hoping eventually maybe to sort of reconcile. I think we're reaching the point where we have enough complexity to at least get into these kind of issues, even though we won't have the real thing, because, well, I know what it will look like if I take the spectrum of the real thing. I can do that in water, and you don't get any information about it, right? You lose all of that if you're trying to do it in exactly the way that it's happening, right? That's why it's difficult. That's why you have to take another route, right?
To sort of follow up what the first question Sam asked, but a little more specifically, for the first part of the talk you gave, you saw the ruthenium dioxygen species. So can you actually do something to see what will happen to it if you further react it? Because you go back to that, can you show the reaction?
Yeah.
Can you actually probe and see if something what they propose here could be happening? Yeah.
The thing is, the next step is well, I can probably probe the exchange with the water, but if you're talking about an electrochemical step, then it's become hard. It's hard to do electrochemistry in the gas phase, okay? And you can imagine why. But it exists, right? People do electron transfer. You can do electron transfer dissociation. It's hard to do it in a nice control way, because I would like to be able to have the exact right potentials and so on. Usually you have a reaction.
Yeah. Can you show that cycle again?
Oh, yeah, the oxo, yeah.
Not all of them are.
Not all of them are. It's going to be.
I'm not familiar with that particular cycle. Maybe shadow is. Yeah, actually, there's one right there.
Right there. Yes, you're talking about, for example, this. Yeah.
Can you take a water shell and heat it up?
We have this, but this one is hard because we have a hard time because of all these isotopes, and it's not a lot of it, to separate it from the other one. And I think if we want to do that cleanly, it's going to be, we're looking into a way to actually form something like that from a gas phase reaction, peroxide or something like that. And I think it's going to be a lot more efficient. And once we get there, and if we have all these traps, first trap, you form your species, second trap, you put your water, and so on. Exactly, right? That's why we're doing it, right? Because now you can think about these kind of experiments. I would love to be able to do electrochemistry. It's much harder problem to transfer electron in and out in a controlled way. But, cannot do everything in the gas phase, I guess.
It's convenient to have this slide up, since I was going to ask, in addition to looking at the OO stretch, can you look at the metal oxygen stretch? And related to that, how low in energy of a transition can you go before, once again, you run into the problem of photons not being enough to break the bond?
Yes. Very good question. The first one, how low can we go right now, is limited by our laser, okay? And I think I have the spectrum here. Power at 700, it's, pretty much zero, okay? And so that's sort of a technology thing. The binding energy of the tag, it varies depending on your ions, but it's usually in the order of 400, 500 wave number, okay? I like to give energy in wave number because it makes sense. And so, yeah, you would run into a problem here where you would start, but that would be if your molecule is at 0 Kelvin. And in reality, our molecules are not at 0, they're not even at 10, they're probably around 30, 35. And so you can probably go lower than the binding energy because you already have internal energy. Most of these ions are just on the cusp of dissociation. Any energy you put in, you're going to see some dissociation, right? The problem is, can we get a laser, right, that would go all the way down to see metal oxygen. There will be around 500-600 wave number, and so on. If you have a free electron laser, you can do that. You can go down to 100 wave number. I don't have one. That's why I would like to do Raman spectroscopy, right? Because then you're not limited by all low you can get. It's the difference between two things. But then that's a nonlinear thing, and that's a whole other can of worm. But that's part of getting better to be able to start thinking about this. We need an action Raman scheme, if you want. Okay, so that would be, I think, very interesting for other metal species, where the interesting thing is usually at low frequency. Was there another one?
Etienne, I had a question, more like a comment. Maybe if you can show us again the triglycine spectrum. I think it was exciting to see that when you add one molecule of water, there were these dramatic conformational changes.
Yes.
Did you show us anything that happens when you add extra molecules of water?
Well, this is right now, so we're just starting to do this experiment and hitting all kind of stuff. But this is the first case in which we see a dramatic change in the function of solvation. The diglycine, you can add water on it, and all you do is add water. But it makes sense. It's not an extremely flexible thing, right? Here it becomes very dramatic. And so we haven't been even looking at larger cluster here because we're still trying to solve that riddle over here. I think we have a pretty good idea. It looks like, from what we have so far, that one water is enough to correct these kind of anomaly, which is that weird pronation site and that cis amide. Actually, adding one water is enough to do that. And now this is the other riddle. I don't know how we switch that around so easily. This is supposed to be really hard to do, right? This is a very high barrier. That's why it's very slow in solution. This is like 80, 90 kilojoule per mole. It seems to be happening very rapidly and under desolvated condition, which I don't quite understand yet. But this is last week.
The reaction itself is happening at the higher temperature, and then you freeze it.
Yes, and the thing is, because of the way we're doing things in isolation, you have to think slightly differently than in solution, because we're not in constant equilibrium with the bath, if you want, right? And so there is some buffer gas, but that's slow cooling. So you can imagine that a water and the ions, and they come together, okay? You gain essentially the binding energy in internal energy, right? Because it takes a little bit of time for it to dissipate. And so every water you add comes with quite a bit of energy, right? And that's enough to wiggle, find a new minimum and stuff like that. We haven't been able to completely characterize that, and we need to get better at really understanding exactly what we have under these kind of conditions to get barriers and so on. We've done some experiment where we change the temperature of the trap, and we can see a reaction change the function of temperatures and so on. So we know, we can thermalize things, but then if you try to think of what is happening exactly, you have to take into consideration that equilibrium with the bath is very slow, right? So that gives you a lot more time to do stuff.
What's the upper limit of the molecular size you can handle with stereoplastic?
The biggest one that I personally ever did was the one I showed you earlier with the vancomycin, right? And the limit is essentially a mass resolution, because you're looking at the loss of a tiny little D2 on top of something that is huge, okay? So you need very good mass resolution to do that. And that is usually the limit of our mass spectrometer. Is not as good as, what you get at commercially. But if we get better at doing that, I don't think there is an intrinsic limitation in size, right? You could do that with whole protein if you want, as long as you're able to resolve losing a D2 on top of a protein, okay? Or mini D2 or something.
Sorry.
Have you tried looking at just standard Gaussian output in normal modes in that region from like 3,000 to 3,600 to get any insights as to what's going on?
Oh, yeah. Well, I'm going to tell you what's happening here. if you keep that secret, okay? All of these, there's that, all of that. That's one thing. That's one OH stretch, okay? Because if you put a D2O, all of that move away. But it's all the same, because if you try to burn every single one of these peaks, everything disappears. Coupling with low frequency mode of the water and something like that.
Right, with that we can end by